Let's talk of the last and the most recent, probably, addition to the subdisciplines of physics, quantum mechanics. We are in the 100th year of the discovery or the proposal of quantum
1925 to 2025. Yes, you're right.
In 100 years, it's come from a theory that a handful of people understood to where we now have regular people in a society talk of some benefits they can derive. There's probably no scientific discipline that has gone so fast into popular lexicon. So
Yes.
tell us a little bit about where the prospects are. What is it that we can see happen directly due to quantum mechanics? I mean, we all know that satellites are able to communicate largely due to quantum mechanical effects, and there are other areas where quantum mechanics has already made a difference. But more tangibly, more specifically, what are the sort of the high-level benefits?
To take you from what you said initially, from a subject that everybody said only he understands or she understands, right? I don't understand, go and ask him. To something which has become so common. I mean, it's an astonishing journey. In fact, if you ask me, quantum mechanics is everywhere because it's the way we understand matter and interactions, right? So quantum mechanics is a refinement of all the things that we knew so far at that time. Classical physics became understood in quantum mechanical terms. So quantum mechanics is everywhere. A big body like you and me can also be explained by quantum mechanics. Maybe it's not needed because there are simpler ways of understanding it. So quantum mechanics is everywhere because it's a part of nature, right? The way we understand nature is through quantum mechanics. But of late, the manifestations that became very obvious are because of the fact that, several fundamental concepts, this belief that, this proposal that quantum behavior is inherently different from classical behavior. Quantization can also exist in classical physics. I mean, you have boundary conditions that leads to quantization. But this business of entanglement, the fact that there's information that is coded in a particle and the particle subdivides, and the information on one can be known by making measurements on the other. It's a fascinating concept. And this is the reason why entanglement has driven, as I said, as a fundamental concept, and also in condensed matter now, and even in, I think, I may be wrong, but I hear even people talking about entangled on a large scale in the universe, right? Things are entangled. So some concepts have become so common because this is a fascinating concept. And the reason I think this entanglement is something that is going to, it's very enriching, very difficult to grasp for a common person. But this is the heart of lots of quantum things that we do, whether it's computing or cryptography, conveying information to information processing and so on. So you can have a quantum key. Again, my knowledge is very peripheral. So quantum keys that will make sure that nobody else can eavesdrop. And lots of work going on at TIFR, even in this and elsewhere in the country. And now even I believe the defense establishments are interested in this. So, for example, much of the big things that we see, satellites being launched, they can all be beautifully, you see the trajectory when ISRO launches a satellite. And I used to see with fascination, the curve exactly goes like what we predicted on the screen. And then there's a huge amount of applause when scientists are elated that it has been placed in the orbit. So much of that is classical physics. And you don't need quantum mechanics to describe such a huge object. But quantum mechanics works for you, whether it's huge or small. But in the micro and nano and pico realms, you need quantum mechanics to predict the correct behavior, right? Even if you don't understand all the implications, you use the correct quantum tools and you get the correct physics. And that's been proved again and again in the last several decades.